So this would be the third lecture of rotational mechanics. So before we start with rotational mechanics, I'd just like to speak to you for a moment. Okay, for 1 minute, let's say. So most of you are concerned about, sir, what is the correct technique and which technique should I prepare for JW Advanced? Not technique. See, let's clear one thing for certain. Okay, technique, that means you're concerned about efficiency. Okay, whenever you're searching for technique, what you're actually concerned about efficiency. CI. And the maximum formula, the base formula for efficiency is nothing but about output by input, isn't it? Output means your result, input means your efforts. Now see this formula and apply some common sense. Okay, no amount of technique can help you if your effort is not there. Okay, so your maximum effort is going in searching for technique, what kind of efficiency, or how to prepare, or how to do this, or how to do that. And you are spending very less time on effort or actually solving the questions. Okay, so if you don't give your effort, you are not going to get your output. Okay, no amount of efficiency or no amount of technique can help you. Go from, if you put one out here, you'll get 100 out here. There exists nothing like that. Okay, if you start solving questions, you practice solving questions, and you solve a lot of it, then you'll figure out what are efficient and what are inefficient by yourself only. Your method of preparation are very personal to you, isn't it? Okay, so we'll figure out more of efficiency if you start doing things. Okay, instead of searching on the net of which is more efficient or which kind of preparation will give you more output. Okay, just pick up standard books. Standard books means, for physics I'm telling you, standard books are HCV, irodov, enough. Okay, if you want more, you can do Resnick Halliday for theory, Proto for more questions. Okay, NCRT, see, if you solve HCV, NCRT is already completed. Okay, NCRT exemplar, those are NEET level questions. Okay, so for JEE Advanced, it is assumed that you can do out there or you can apply NEET level questions. But the maximum crux that I'm trying to explain you is, if you don't have an effort or if you don't have an input, no amount of technique can give you output. That's the crux, or that's the fundamental thing of things. Okay, this technique, that technique won't be working. Just start doing your effort or start solving questions. Okay, open the book, see the question, start solving the question. You get stuck, see part of the solution, again try to do it, again get stuck, again see a little bit more of the solution, and then keep revising whatever you have done. Okay, and then you'll figure out, acha, this can be done easily by this method, this can be done easily by this method. You'll figure out this portion of by yourself. Okay, but if you keep skipping this, okay, no amount of efficiency or no amount of gain from internet can help you, this output. Okay, so having said that, okay, your JEE Advanced is on 18th May. 18th May. Okay, so start preparing for it, and your main second session is on April. So let's start with the question. Okay, so in this question, you have to prove perpendicular axis theorem. Okay, perpendicular axis theorem, and perpendicular axis theorem is only valid for 2D bodies. Okay, let's see an interesting way by which we'll prove this perpendicular axis theorem. Okay, so suppose this is the y coordinate or y axis. Okay, and this is my x axis. Okay, this is my x axis, this is my y axis. That means I'm drawing a graph paper. Okay, and this is a 2D graph paper. A point mass, remember, a point mass is kept out here of mass m. Okay, the coordinates of this point mass are, let's say, x1 and y1. Okay, let's say x1 and y1, x1 comma y1. This is mass m1. Okay, this much is understood. This is a point mass of m1. The coordinate of this mass in this xy graph paper is nothing but x1 comma y1. This much is understood. Okay, now my first question is, what is the moment of inertia of this point mass through x-axis? That means this is my axis. Okay, so first question is, this is my axis or this is my x-axis, ix. What is the moment of inertia of this point mass about this x-axis? Ix, or moment of inertia about x-axis, is nothing but mass m1 into this much distance square, and this much distance is nothing but y1, isn't it? This much distance is nothing but y1, because the y coordinate is nothing but y1, isn't it? So moment of inertia about this axis is nothing but m1 into y1 square. Okay, now my next question is, what is the moment of inertia about this axis? or axis passing through y axis. Okay, axis or moment of inertia passing through y axis is nothing but iy. Okay, so moment of inertia passing through y axis is nothing but m1 into this much distance square, isn't it? And this much distance is nothing but x1, x1, because the x coordinate is x1. So this much distance is nothing but x1, and moment of inertia of this point mass passing through y-axis, when the axis is passing through y-axis, is nothing but m1 into x1 square. So m1 into x1 square. Now my third question is, what is the moment of inertia passing through z-axis? That means z-axis is perpendicular to the plane of this one, or plane of paper. Okay, so izz. Okay, izz is nothing but m1. Okay, m1 into this much distance square, and this much distance is nothing but, if I apply Pythagoras theorem, how much is this much distance? This much distance is nothing but under root of x square or x1 square plus y1 square, under root of x1 square plus y1 square. So this much distance is nothing but under root of x1 square plus y1 square. Why? Because if I apply Pythagoras theorem, x1 square plus y1 square is equals to hypotenuse square. Okay, so iz is nothing but mass into this much distance. This much distance is nothing but under root of x1 square plus y1 square whole square. Mass into distance whole square. Okay, or iz is nothing but m into, if I open this up, it is nothing but x1 square plus y1 square whole square. See, this square root and whole square cancels out each other, isn't it? Now iz can be written as m x1 square plus m y1 square, or m1 x1 square plus m1 y1 square. Now m1 x1 square is nothing but how much? Iy. So this is nothing but Iy. Okay, and this one is nothing but Ix, or moment of inertia passing through x-axis, Ix. So I can prove that Iz is equals to Ix plus Iy. Okay, I might have a doubt, sir, but you have proved this theorem for a point mass, but moment or perpendicular axis theorem is valid for all 2D bodies, you know. So what happens if I have a collection of point masses? See, a continuous body can be represented as a collection of point masses. So if I prove that this theorem is also valid for collection of point masses, okay, then it can be valid for any 2D bodies, isn't it? Be it continuous or be it discrete. Okay, discrete means separated out, continuous means connected together. Okay, so if I prove that this theorem holds for collection of particles or collection of point masses in the same plane, that means all my masses should be kept in xy plane. Okay, that means this perpendicular axis theorem is valid for all 2D bodies. Okay, so let's take another body, m2. Okay, x2 y2. Similarly out here. Okay, now there are 2 point masses, m1 with coordinate x1 y1 and m2 with coordinate x2 and y2. Now what is my moment of inertia passing through x-axis? Moment of inertia passing through x-axis, it is nothing but m1 into y1 square plus m2 into y2 square. So m1 y1 square plus m2 into y2 square, isn't it? Similarly, what is my moment of inertia passing through y-axis? Moment of inertia passing through y-axis is nothing but m1 into x1 square plus m2 into x2 square. So m1 x1 square plus m2 x2 square. Okay, now similarly, what is the moment of inertia passing through z-axis? Iz is nothing but m1 into this square. So m1 into under root of x1 square plus y1 square whole square plus m2 into this distance, and this distance is also nothing but under root of x2 square plus y2 whole square. Why? Because even I can apply Pythagoras theorem again, no? And this distance is nothing but x2 square plus y2 square. So Iz is nothing but m1 x1 square plus y1 square plus m2 into x2 square plus y2. Okay. Now if I rearrange these terms, okay, m1 x1 square plus m2 x2 square. If I take this term and this term, okay, these two terms, this term and this term, this is nothing but Iy. If I take this term, this m1 y1 square plus m2 y2 square is nothing but Ix. So I can rearrange this term as, or let me erase this one. Okay, if I erase this one, then I'll get Iz is equals to m1 x1 square plus m2 x2 square. I have taken this term, okay, and this term. I'm taking remaining of the term m1 y1 square plus m2 y2 square. Now this entire term is nothing but iy, and this entire term is nothing but ix. So I can easily see that moment of inertia through z-axis, even for a collection of particles, is nothing but moment of inertia passing through y-axis, sorry, x-axis, plus moment of inertia passing through y-axis. If you take the third particle, the same thing can be done out here, okay, and the same theorem would be valid out here. So this perpendicular axis theorem is valid for all 2D bodies, be it separately allocated 2D bodies or discrete 2D bodies or a continuous 2D bodies. As long as the body is 2D or two-dimensional, perpendicular axis theorem is applicable out here. Okay. So this was our question number 240. So this question is nothing but you have to find out the moment of inertia of this shape about the center of or center of mass of this object. Okay. So the first part, I'll try to find out the moment of inertia about the center of the disk. Okay. Moment of inertia about the center of the disk. Okay. And to find out moment of inertia about the center of the disk, that means about the axis passing through point O, what should I do? I must apply principle of superposition. What principle of superposition says? Principle of superposition. Superposition. That means the moment of inertia of this entire object is nothing but moment of inertia of the completed disk about point O minus moment of inertia of the empty part assuming it is filled about point O is nothing but moment of inertia of this shape about point O. Okay. My first step is finding out the moment of inertia of this entire thing about point O. So step one, moment of inertia about point O. I'll go again. Okay. This question is asking find the moment of inertia of this shape about the center of mass of this shape. Okay. So my first approach is I must find out the moment of inertia of this shape about point O. Okay. This point O is not the center of mass of this shape. I'll find out the center of mass of this shape later. Okay. I'm just finding out the moment of inertia about this point O. Okay. And to find out the moment of inertia about this point O of this entire shape, I must apply principle of superposition. What principle of superposition says is that moment of inertia of this shape about point O is nothing but moment of inertia of the completed shape, okay, entire disk filled about this point minus moment of inertia of this empty part. This empty part assuming it is filled about point O. So these are point O, point O, point O. Okay. Now let me do if this entire part is radius r. Okay, this entire part is also radius r, isn't it? So the half of radius r is nothing but r by 2. So radius of the smaller circle is nothing but half of radius of the bigger circle. This much is done. Okay, so this is r, this is nothing but r by 2. R by 2. Okay, let the mass of the entire shape, assuming it is complete, be capital M. Let the mass of the small shape be small m. Why am I doing that? Because it will be much easier. Okay, so moment of inertia about point O is nothing but m r square by 2 because this is the disk. Moment of inertia of this small shape is nothing but m r square by 2. Let this r by 2 be written as small r. Okay, I'll substitute later. This small r is nothing but the radius of the empty part. This small r is nothing but the radius of the empty part. And this small r is equals to capital R by 2. This small r is equals to capital R by 2. Why? Because this entire thing is the diameter of the hollow part and half of diameter is nothing but R by 2. Okay, because the diameter is nothing but radius of the twin disk. Okay, and I'll assume this R by 2 to be another variable smaller. So the moment of inertia of this small hollow part, assuming that is filled, is nothing but m r square by 2. M r square by 2. But when I write this moment of inertia m r square by 2, I am finding out the moment of inertia of this entire thing about the center of hollow part, no? Okay, about the center of hollow part, isn't it? But I must find out the moment of inertia of this object about point O, isn't it? About this point O. So I can apply parallel axis theorem out here, and the moment of inertia about this entire shape about point O is nothing but moment of inertia about the center plus mass of the entire object into perpendicular distance between center and the new axis. And the new axis is nothing but axis passing through O. So mr square. Okay, so moment of inertia of this entire object about point O is nothing but 3 by 2 mr square. 3 by 2 mr square. You understood this much part? This much part is nothing but moment of inertia of this hollow part about point O. Mr square is nothing but moment of inertia about the center. And if I want to find out the moment of inertia about point O, I must apply parallel axis theorem out here. Okay, this is nothing but parallel axis theorem. Parallel axis theorem. Understood? This much is understood. Okay. So moment of inertia of this entire object is nothing but this moment of inertia minus this moment of inertia. So moment of inertia of this entire object about point O is nothing but a mass square by 2 minus 3 by 2 m r square. Okay. So this is nothing but the answer. Now just play with variables and find out the answer in terms of mass of this object and things like that. Okay. Because this mass m is nothing but the mass of the entire disk assuming it is filled. This mass small m is nothing but mass of the hollow part assuming it is filled. So I must convert these masses and this radius in terms of mass of this object and radius of this object. Now how do I do that? First I must transform this answer in terms of density. Okay. First part is transform this answer in terms of density. Transform this answer in terms of density. Why am I doing that? We'll understand it in a moment. Okay. So, okay. Moment of inertia is nothing but m square by 2 minus 3 by 2 m square. So, let the density of this object be rho. Okay. Let the density of this object be rho. Rho is nothing but density of disk. Density of this disk. Okay. So density of this entire disk is equals to density of this filled disk, which is equals to density of the hollowed out part assuming it is filled. Why? Because all the material is made up of same thing, isn't it? Every material out here is made up of same thing. That's why everything will have the same density, isn't it? So density is equals to mass of the entire thing, mass of this entire thing, which is nothing but m, okay, divided by area of the entire thing. Area of the entire thing is nothing but pi r square. Pi r square. See, I'm finding out planar density or areal density. Okay, this is not volumetric density. This is planar density. That means mass divided by area. Planar density is nothing but mass divided by area. Okay, so mass divided by area of this circle should be equals to mass divided by area of this circle, isn't it? Because everything is made up of same material. Okay, which is equals to mass of the smaller part divided by area of the smaller part, isn't it? Area of the smaller part, which is equals to mass of this part divided by area of this part, which is equals to, let the mass of this part be another variable, let's say m, okay, or m dash. M dash. Mass of this is nothing but m dash. Okay, m dash is given as 7.3 kg object. Okay, which is equals to mass of this shaded part divided by area of the shaded part. Let the area of the shaded part be a dash. Okay, area of the shaded part. Understood what I did out here? Okay, and the moment of inertia of this shape, okay, of this shape about center point is nothing but we have already found out m r square by 2 minus 3 by 2 m r square. So m r square by 2 minus 3 by 2 m r square. M r square. And this mass is nothing but mass of this one. Okay, this mass is nothing but mass of this one. Okay, so out here, okay, out here I must either convert this small m in terms of capital M or capital M in terms of small m. Okay, I must have only one pair of variable, either capital M and capital R or small m or small r. You decide which one is which. Okay, both methods will obtain the same answer. But I'm going with capital M and capital R. That means I must transform this small m and small r in terms of capital M and capital R. Okay, so out here it is nothing but transform m r in terms of capital M and capital R. And how do I do that? I am using this relation. Okay, this relation, density of all the materials are same. So if I just pick out first two terms, okay, first two terms means m by pi r square is equals to small m by pi r square. Pi and pi will get cancelled. Small m is equals to capital M by r square into r square. Now if I just replace this small m out here, what do I get? Moment of inertia I is equals to m r square by 2 minus 3 by 2. What is the value of m? Value of m is nothing but m by r square into capital R square. One more thing, small r is nothing but capital R by 2. I've already said that before. Small r is nothing but capital R by 2. So let me again, m is equals to m r square into capital R by 2 whole square. Okay, r square and r square will get cancelled. 2 square is nothing but 4. or AM is equals to capital M by 4. Okay, so 3 by 2 capital M by 4. Small m is nothing but capital M by 4. I have written this small m out here into r square. R is nothing but capital R by 2 whole square, isn't it? Or moment of inertia is nothing but AMR square by 2 minus 3 by 8. 3 by 8 into AMR square by 4. Okay, or moment of inertia is nothing but AMR square by 2 minus 8 3 sorry 8 4 32. 3 by 32 MR square. Okay, okay, by 4 and by 4. So 4 is 8. Okay, or if I take MR square common, 1 by 2 minus 3 by 32. Okay, I take the LCM as 32. 2 into 16 minus 3. 16 minus 3 is nothing but 13 by 32. So moment of inertia is nothing but 13 by 32 capital M R square. Capital M is nothing but mass of the filled out disk. Okay, understood this much? Capital M by R square. Now I must transform this capital M in terms of M dash. Why? Because the mass of the shaded part is given, isn't it? Okay, so how do I do that? I use this relation and this relation. Okay, so before that I must find out what is the area of the shaded part. So area of the shaded part is nothing but area of the entire part, which is nothing but pi r square minus area of the hollow part. Area of the hollow part is nothing but pi r by 2 whole square, or area of the shaded part is nothing but pi r square minus pi r square by 4, or area of the shaded part is nothing but 3 by 4 pi r square. Okay, if you take pi r square common out here, it is nothing but 1 minus 1 by 4. 1 minus 1 by 4 is nothing but 3 by 4. So area out here, or area of the shaded part, is nothing but 3 by 4 pi r square. So area of the shaded part is nothing but 3 by 4 pi r square. Now if I take the first term, m divided by pi r square, and this last term, m dash divided by 3 by 4 pi r square, I can write it as m divided by pi r square is equals to m dash divided by 3 by 4 pi r square. Okay, pi r square and pi r square will get cancelled, or m dash is nothing but 4 by 3 m. Okay, or mass of the shaded part is nothing but 4 by 3 part of the, wait a minute, 3 by 4, not 4 by 3. Why 3 by 4? If you just take this 3 by 4 and multiply it to the left, it is nothing but 3 by 4. It's not 4 by 3. I just made a calculation error out here. Okay, don't do that. So m dash is nothing but 3 by 4 capital M. So m dash is nothing but 3 by 4 into capital M. Don't make the mistake that I made out here. Okay, silly mistakes. So that now m dash, or mass of the shaded part, is nothing but 3 by 4 times mass of the disk assuming entirety was filled, isn't it? Or 3 by 4 m. Now I must convert this capital M in terms of m dash, because this mass of the shaded part was given in the question. No, m dash was given by 7.3 kg, isn't it? So, or capital M is equals to 4 by 3 m dash. Okay, I must replace this m out here. So moment of inertia is nothing but 13 by 32 into m dash, or 4 by 3 m dash into r square. Okay, 8 4 is 32, 8 3 is 24. Okay, our moment of inertia is nothing but 13 divided by 24 into m r square. Okay, understood? The moment of inertia of the entire disk is nothing but mass of the shaded part into 13 by 24 into r square, radius of the bigger disk. Okay, so this entire moment of inertia that I found out here, okay, that I found out here, is nothing but moment of inertia about the axis O. Okay, the question is asking find out the moment of inertia about the center of mass of this object. Okay, so first thing I must find out is the center of mass of this object. Now what you have to do is you have to find out the center of mass of this shaded part. Okay, so you have to find out center of mass of shaded part. Okay. From the diagram you can see if this point O is considered as my origin. Okay, I'll find out my center of mass considering this point O as origin. Okay, if you look at the y-axis, the upper part is symmetric to the lower part. That means the y center of mass will be along this line only, isn't it? Because the upper part is symmetric as lower part. So the y center of mass will lie along this line only. Okay, I'll find out the x center of mass. So x center of mass is nothing but mass of the entire shaded part, which is nothing but m into x coordinate of the entire shaded part, which is nothing but 0, isn't it? Minus mass of the empty part. Mass of the empty part is nothing but small m into x coordinate of the center of mass of x coordinate of the entire shaded part or empty part. This is nothing but minus r by 2. Minus r by 2 divided by total mass m plus m. Now, those of you are confused how I did this formula, center of mass is what? Mass of element 1 plus mass into coordinate of element 1 plus mass of element 2 into coordinate of element 2 plus mass of element 3 into coordinate of element 3 divided by entire mass m1 plus m2 plus m3. And if you are applying subtractive method, mass of the entire thing into center of mass of the entire thing minus mass of the hollowed out part into center of mass of the hollowed out part, isn't it? Divided by total mass. I've done this in work energy theorem, isn't it? So x center of mass is nothing but 0 minus and minus becomes plus mr by 2 plus mr by 2 divided by m plus m. Now let us convert this entire small m into capital M. So the relation between small m and capital M is nothing but, let's see, where is the relation between small m and capital M? Achha, out here. Okay, from this relation I'll get, from this two equation I'll get small m is how much? Small m is equals to capital M by 4. Look out here. Okay, small m is equals to capital M by 4. So x center of mass is equals to capital M by 4 into r by 2 divided by m plus small m is equals to capital M by 4, or x center of mass is nothing but mr by 8 divided by 4 to the 8 divided by m plus m by 4 is nothing but 5 by 4 m. So x center of mass is nothing but mr by 8 divided by 5 by 4 m, 5 by 4 m, or x center of mass is nothing but mr by 8 into 4 by 5 m. Then m and m will get cancelled. 4 to the 8, so we'll get x center of mass is nothing but r by 10. R by 10 was right. So at distance, this distance at r by 10, isn't it? At r by 10, this will be the center of mass, and the distance from the point O is nothing but r by 10. Okay, and we have to find out the moment of inertia of the entire shaded part about this point. Okay, about this new point. This, let's name this star. Okay, about this new point star. That means my axis is passing through star. Okay, so can I apply parallel axis theorem out here? What I'm trying to say is, if I apply parallel axis theorem, what does parallel axis theorem say? Center of mass of any body is nothing but center of mass passing through the center of mass. Sorry, moment of inertia passing through the center of mass. Moment of inertia passing through new axis is nothing but moment of inertia passing through the center of mass plus mass of the object into perpendicular distance between the axis square, isn't it? This was the parallel axis theorem. Okay, what is the moment of inertia passing through the center? I don't know, I have to find out. Okay, what is the acha, this is nothing but, this star is nothing but moment of inertia passing through the center. Okay, I did some, okay, let's name this IC, a center. This is nothing but the center. Okay, now moment of inertia of O. See, you all know this parallel axis theorem. Moment of inertia about new axis is equal to moment of inertia passing through the center plus mass of the object into perpendicular distance between the parallel axis, isn't it? So this is nothing but I have to find out. I have to find out in the question. I star. I star is nothing but moment of inertia passing through O. Why is that? Because I already know the moment of inertia passing through O, no, point O. What is the moment of inertia passing through point O? Moment of inertia passing through point O is nothing but 30 by 24 mr square. See out here. So moment of inertia passing through point O is nothing but 13 by 24 m dash r square. See out here, 13 by 24 mr square. Okay. Now you might ask, sir, why haven't you done out here 13 by 24? See, parallel axis theorem is nothing but both the axes must be parallel. So center of mass through one of the axes, sorry, not center of mass, moment of inertia through one of the axes is nothing but moment of inertia passing through the center of mass. Okay, that means this axis must pass through the center of mass plus mass of the entire object into perpendicular distance between the axes. Okay, this is mass of the object into perpendicular distance is nothing but r by 10. I have already found it out, isn't it? So r by 10 whole square. So moment of inertia passing through the center is nothing but, if I send this mr square to the left hand side, I'll get this term minus this term. So 13 by 24 m dash r square minus m dash r square by 10 square is nothing but 100. So if I take 100 m r square common, moment of inertia passing through the center of mass is nothing but m dash r square 13 by 24 minus 1 by 100, isn't it? Now if I take the LCM and do it, if I take the LCM and solve it, I'll get the moment of inertia passing through the center of mass. Okay. One thing you must remember is point O is not the center of mass of this shaded part. Okay. So the center of mass of the shaded part is out here at this point. Okay. And parallel axis theorem states that moment of inertia about this axis is equals to moment of inertia passing to the center of mass, that means about this point, plus perpendicular distance, means plus mass into perpendicular distance between the axis square. So this I already know, but this is nothing but the moment of inertia passing through point 2. I have already derived in the previous slide. Okay, 13 by 24. I have to find out moment of inertia passing through the center of mass, this one. So this one is nothing but this value. Just solve it and find out the answer. Okay. There's a little bit of error that I made out here. So when you're finding out center of mass, okay, center of mass is nothing but m1 into location of mass 1 plus m2 into location of mass 2 plus m3 into location of mass 3 divided by total masses m1 plus m2 plus m3 plus m4. But out here, when I'm finding the center of mass of this shaded part, what I'm doing is I'm doing subtractive thing. That means I have assumed that the whole thing to be filled and have to eliminate this much part of the mass from this entire circle, isn't it? So it is nothing but mass of the whole circle into center of mass of the whole circle. So m into 0, isn't it? M into 0 is nothing but mass of the whole circle into center of mass of the whole circle, which is nothing but 0. Our point O is considered as origin, so 0. Minus mass of the hollow part or mass of the part that is white, isn't it? Into center of mass or coordinate of center of mass of this white portion, isn't it? This one divided by total mass. What is total mass? Mass of the entire thing minus mass of the white part. So instead of plus out here, I have to do minus out here. Understood? So the error that I made out here I made plus out here. Okay? So it should be minus out here. M minus. So m minus m by 4 is nothing but 3m by 4. So instead of 5m by 4, it would be 3m by 4. Okay? And out here also it should be 3m by 4. Okay? M divided by 3m by 4. Okay? Now let's calculate the entire thing. X center of mass. X center of mass is nothing but mr by 8 into 4 by 3m. 4 2s are 8. Okay? And m is in denominator. And m would get cancelled out here. So it would be r by 6. So the center of mass is not r by 10, it is r by 6 out here. Okay? R by 6. Fair and fine. Now we'll apply parallel axis theorem out here. Okay? So out here 13 by 24 m r square plus passing through the center is equals to mass into out here instead of r by 10, I have to substitute by r by 6. Okay? Or r by 6 whole square. R by 6 whole square. So let me erase this one. Okay? So IC is equals to how much? 13 by 24 m r square minus m dash r square by 6 is nothing but 36. So if I take IC is equals to, if I take m r square common, m r square common, it is nothing but 13 by 24 minus 1 by 36. So when you solve this answer, we get the answer that is in this question. The error that I made out there is nothing but making it plus out here. So instead of being plus, it would be minus. Why? Because I'm finding out moment of inertia by subtracting this white part, isn't it? What is the formula for moment of inertia? Mass 1 into coordinate of 1 plus mass 2 into coordinate of 2 plus mass 3 into coordinate of 3 divided by total mass, isn't it? So while I'm doing uh, subtractive kind of thing, where I have to find out the center of mass of the shaded part, what did I do? Mass of the entire circle into center of mass of the entire circle minus mass of the white part or mass of the missing part into center of mass of the missing part divided by total mass. Total mass is nothing but mass of the whole circle minus mass of the missing part, isn't it? So this was the thing that I made out there. Okay. Now in this question, we have to find out the moment of inertia of a thin spherical layer. Thin spherical layer means spherical shell. Spherical shell. And I have already done the derivation of spherical shell. moment of inertia of a spherical shell is nothing but 2 by 5, sorry, 2 by 3 mass of the spherical shell into radius of the spherical shell whole square. This is already done in the class. See, in this question, the question is specifically asking to derive from solid sphere, but that purpose is not that much in your syllabus. Okay, and that is very unintuitive also. That means you have to write out the moment of inertia of a spherical solid sphere is nothing but 2 by 5 m square. Then you have to differentiate, and you do not get the intuition of how moment of inertia works. So I have shown you the derivation of spherical shell. Just follow it. Okay, in the previous lecture. Just go to the previous lecture and see there is a lot of derivation done. Okay, one of them is nothing but moment of inertia of a spherical shell. Now, whenever you have this kind of question, okay, the first instinct should be, see, out here there is a mass m, okay, and there is a disk, okay, and this disk has mass capital M. Now, when this small mass m or when this block is coming down, one thing to note out here is in your earlier problems or in your problems of Newton's laws of motion, while you were solving for pulley system, the main assumption was pulley was not rotating. That means there was no friction force between the rope and the pulley. Okay, but out here in the chapter of rotational dynamics or rotational mechanics, whenever you solve pulley problem, out there it is assumed that the pulley has some mass and there is some friction between the rope and the pulley, and this rope rotates the pulley. Oh, sorry, this friction rotates the pulley. I have to solve it like that. So the situation or the method of solving the question will be same as Newton's laws of motion. You have to draw out the equation, okay, and solve it. The problem out here is there are two kinds of equation out here. Okay, linear equation, that means Newton's laws of motion equation, and rotational equation. So first one is linear equation. Make a linear equation and solve it. Second one is make a rotational equation and solve it. And the third portion of this kind of problem, or whenever there is mechanics problems, is rotational mechanics. Okay. First step is to figure out the linear equation. Second step is to figure out the rotational equation. The third step is to figure out the parameters between or the relation between linear and rotational variables. Relation between linear and rotational variables and rotational variables. Okay. So let's start with first part. Okay. Linear equations or linear equation. First part is linear equation. Let me just copy this diagram out here on the next page. Okay. Okay. If you see this diagram, this mass M, okay, if I draw the free body diagram of this pulley, this mass M is being pulled down by mg force, isn't it? Gravity is pulling this mass M down, and a tension force of T is applied on this mass, and let it has some acceleration A. Okay, so the linear equation can be written as mg minus T is equals to mg minus T is equals to m into A. Okay, where A is the nothing but the acceleration of the block. A is nothing but acceleration of this block. Okay, now one more thing. Now let's go to the rotational equation. Rotational equation. The rotational equation will be done by studying the pulley itself. So out here is the pulley. Okay, out here is the pulley of mass M, and there is a tension T out here. Okay, so if I apply a tension T out here, the pulley is supposed to be rotate, no? The pulley is supposed to rotate. Let's say with angular acceleration alpha. Okay, so this force T produces a torque in the cylinder, which makes it rotate with angular acceleration alpha. So torque in the center of the disc. Okay, I'm considering the center of the disc as my axis. Okay, so torque through the center of the disc is nothing but T into R or R cross T. Out here, I'm applying the or I'm studying the torque. Torque is nothing but torque due to force tension through the center of the disc. That means out here is my origin. Okay, so torque is equal to nothing but R cross T, a distance from the origin cross T, the force tension, isn't it? Is equals to moment of inertia of the disc, moment of inertia of the disc into angular acceleration of the disc, into angular acceleration of the disc. Okay, now this is a solid cylinder, so moment of inertia is nothing but m r square by 2. Moment of inertia is nothing but m r square by 2. So I'll get my equation as T into R is equals to m r square by 2 into alpha, where alpha is the angular acceleration. Or I'll get T is equals to capital mr by 2 into alpha. Okay. Now the third part. the relation between linear and rotational variables. Okay, see, if this body is moving down with angular acceleration a, that means look at this point. Okay, this point, the instantaneous acceleration of this point is also a in downward direction. No, the instantaneous acceleration of a is, or this point is also a in downward direction. Okay, so can I find the relation between angular acceleration alpha and linear acceleration a? Of course I can. A is equals to alpha cross r, isn't it? Or a is equals to alpha into r. A is equals to alpha cross r. The angle between alpha and r is nothing but 90 degrees. So sine 90 is nothing but 1. So A is equals to alpha r. Okay. So then fine. Now if I substitute this alpha with A by r, out here I can rewrite this equation as A by r is equals to alpha. No. So I'm substituting this alpha out here by A by r. Okay. So I'll get my equation as T is equals to m r by 2 into A by r. Or r and r will get cancelled. T is equals to m a by 2. Okay, this is the third equation that I get. Now solving this first equation, this second equation, okay, and the third equation. Okay, solving this first equation and second equation, I'll get the value of acceleration. Okay, let me check. Okay, substituting this value of t out here at mg minus t. This is simple equation solving, nothing more, nothing less. Ma by 2, okay, is equals to mass into acceleration. What I did out here is I just took this value of tension T out here. Okay, this tension T out here was replaced by T out here. Okay, and we get mg minus T. This T out here is nothing but the tension force that was obtained out here. Okay, minus tension force is equals to mass into acceleration, isn't it? So if I send that mg is equals to ma plus capital Ma by 2, where capital M is the mass of the cylinder and small m is nothing but mass of the block. Okay, or mg by m plus capital M by 2. Okay, mg is equals to acceleration of the block. Okay, so this is our first part of the answer. The first part of our answer is the angular velocity of the cylinder. Achha. So I found out the linear acceleration of the cylinder. So from this A, okay, I can find out the angular velocity of the disk. How? Because if I find out the linear acceleration, okay, I can find out the linear acceleration out here. If I know the linear acceleration out here, I can find out the angular acceleration. If I know the angular acceleration, I can find out the angular velocity. Okay. So the linear acceleration of this block has been found out. So the linear acceleration of this point has been found out. So can I find out the value of angular acceleration alpha? Of course I can. Alpha is equals to how much? A by r, isn't it? See, alpha is equals to A by r. Okay. So out here, what is the value of A? Mg divided by M plus capital M by 2. Just wait 1 minute. Okay. So alpha is equals to A. The value of A is nothing but mg divided by small m plus capital M divided by 2. So mg divided by small m plus capital M divided by 2. This is the value of A divided by 1 by r, or into 1 by r. Right? A divided by r. A divided by r. Okay. So the value of alpha is nothing but mg divided by m plus m by 2 into r. Now look out here. Okay. Is this force mg going to be constant? Force due to gravity is going to be constant. So the tension force is also going to be constant. So if all the forces out here are not varying with time, that means the acceleration out here is also constant. And if acceleration out here is constant, we can follow the 3 laws of kinematics. V is equals to u plus at. Okay. S is equals to ut plus half at square, and v square is equals to u square plus 2s. Okay. And the rotational equivalent of these formulas in rotational mechanics is nothing but final velocity is equals to initial velocity plus angular acceleration into t, isn't it? Then angular displacement is equals to s is equals to ut, initial angular velocity into time plus half angular acceleration into t square, and v square is equals to u square plus 2s. So final velocity square is equals to initial angular velocity square plus 2 alpha into s becomes angular displacement. Okay, I need to find out the angular velocity, okay, with respect to time. So angular velocity, if I take the first formula, final angular velocity is equals to initial angular velocity plus angular acceleration into time. What is the initial angular velocity? It is given in the question. The system is set in motion. That means the initial angular velocity of the system was equals to 0. Okay, which is equals to 0 plus alpha. What is the value of alpha? Mg by m plus capital M by 2 into r. mg by m plus capital M by 2 into r into t. So I found out omega final is equals to, or final angular velocity with respect to time is equals to mgt by m plus capital M by 2 into r. Okay, so this is our angular velocity with respect to time, or angular velocity of the disk, angular velocity of this pulley disk with respect to time. Now the second part of the question, the kinetic energy of the whole system. Okay, we do know the initial kinetic energy. What was the initial kinetic energy? The system is set in motion. That means initially the system was at rest. So initially the kinetic energy of the system was zero. We just need to find out the final kinetic energy of the system, isn't it? So I can apply work energy theorem out here. Applying work energy theorem. Okay, I'm doing part 2 of the question. Part 2 of the question. Applying work energy theorem. Change in kinetic energy is equals to acha. In work energy theorem, it should be see. Change in kinetic energy is equals to work done by all the forces and all the torques. Okay, work done by all forces and all torque. Where work done by force would be equals to force into displacement. Work done by torque would be torque into angular displacement. Okay. So final kinetic energy minus initial kinetic energy. Initial kinetic energy was zero. Now let me check what are the forces and torque out here. Okay. mg is one force, tension is another force. Okay. And since we already calculated tension as a force, I do not to take this torque due to tension, because torque due to tension was applied by this tension force, no? So tension force and mg force. Okay. If there was an external torque applied by someone else, okay, then you have to take work done by torque also. Okay. But right now, since the torque was applied by this tension force, okay, and I am simply taking the work done by tension force. Okay. So there are two forces out here, mg and tension. Work done by mg force plus work done by tension force. Okay. One more thing. If you observe this diagram, okay, tension force is an internal force. What I mean by that is, see, out here in this downward direction or in the block, tension force would act upward. Out here, the tension force would act downward. Internal force means the work done by tension force out here would be negative of work done by tension force out here. That means the total work done by tension force would cancel out itself. The work done by this tension force on this block would cancel out the work done by this tension force on this pulley. Okay, you might say, sir, out here this tension force is being, or this tension force is being studied as a torque, and that torque is doing work. Fair and fine. The work done by tension force on this block is being cancelled out by torque by this tension force on this block. Okay, both the work will have same value. So that is why tension is an internal force, and the work done by internal force on the entire system is zero. Why? Because the torque or work done by tension force on this body is equals to work done by tension force on this body, or negative of work done by tension force on this body. Understood? So that's why internal force or work done by internal force cancels out each other in a system. If I study this body separately, then the work done by tension force would not be cancelled out. Understood? But since I'm studying the entire system and tension force is an internal force, the work done by tension force gets cancelled out. Okay. So work done by tension force is zero. Okay. Work done by gravity force. Work done by gravity force is how much? Mg into displacement, or mg into h. I don't know the displacement. Okay. So final kinetic energy is equals to mgh. Fair and fine. Okay. Now problem is I must figure out this height h. Okay. Height h, or distance traveled by this block. Okay. As a function of time t. Okay. That means what is the time taken by this block to move distance h downward. I can simply apply this formula. Okay. S is equals to ut plus half at square. I know the value of a. So if I do S is equals to ut plus half at square. S is nothing but h out here. Initial velocity is nothing but 0 plus half the value of acceleration is nothing but mg divided by m plus capital M by 2. Mg divided by m plus capital M by 2, isn't it? Let's see. Mg divided by m plus capital M by 2. Okay. Half a t square. T square. Or we get our height out here as, or height is equals to half mg divided by m plus capital M by 2 into t square. Now if I just substitute this height out here, I'll get my answer. So final kinetic energy is equals to mg into half mg divided by m plus capital M by 2 into t square. So this is my answer. Okay. So in this question, there is a Maxwell disk. Okay. So the first question that I have is, what is a Maxwell disk? It is nothing but, suppose a rod. Okay. There is a rod and two ends of the rod are wound by a string. Okay, in the same manner. It means the string is going behind the rod and winding it up. Okay. And in the center of this rod, there is a disc. This setup is known as Maxwell disc. Okay. Now these two strings might be attached to something, might be attached to a wall, might be attached to a slab. In this question, it is attached to another bar. Okay. See, a string is wound in both sides. Suppose I leave it, what will happen? The string will roll down, or the Maxwell disc will roll down, isn't it? In this question, what is being asked is this body, okay, this bar is moving up with such an acceleration, okay, this Maxwell disk is kept loose. Kept loose means it is kept from rest or started from rest. Okay, it will start rolling down. Now this body is moving up with an acceleration A such that the acceleration of this Maxwell disk is zero. That means when I see this Maxwell disk from the ground, it neither moves up nor moves down. We have to find out the angular acceleration of this Maxwell disk. How do I do that? Let us first find out the tension in the rope. Tension in the rope. So if the mass of this Maxwell disk is m, can I write 2t is equals to mg, isn't it? Or 2t minus mg, 2t minus mg is equals to mass into acceleration of Maxwell disk. Now the acceleration of Maxwell disk is nothing but 0, isn't it? So acceleration of Maxwell disk is nothing but 0. From this equation I get 2t is equals to mg, or t is equals to mg by 2. Okay, understood this much? So we find out the value of tension force. The value of tension force is mg by 2. Now if I rotate this Maxwell disk in this view, that means Maxwell disk is like this, I'm seeing the Maxwell disk like this, okay, from this view. So let me draw the disk. It is a smaller cylinder, let's say of radius r, and the center is a larger cylinder of some other radius capital R. And the string is wrapped, okay, along the cylindrical rod. That means along this R on the both side. Okay, on the back side also it will be wrapped like this. On the front side also it will be wrapped like this. The value of tension force is nothing but mg by 2. I'm just seeing this setup, the same setup as like this, okay, from side view. And I must find out the angular acceleration of this one. So when this is left, okay, or when this is let go, this Maxwell disk is supposed to rotate with angular acceleration alpha. I have to find out the angular acceleration alpha. Okay. Now see, the acceleration of this entire Maxwell disk or this entire setup is equals to 0 from ground frame of reference. Okay, and this bar or this slab is moving up. Okay. Now observe this point, the point which is attached to the rope at the side of the disk. Observe this point. What is the instantaneous acceleration of this point? The instantaneous acceleration of this point would be capital A, sorry, A in upward direction. Why? Because if the rope or if this bar is moving in upward direction, out here, this rope, okay, or a point in this rope would also tend to move in upward direction. See from the frame of reference of this disk, okay, put your observer in this disk and just see the case. If this bar is moving away with acceleration, yeah, A in upward direction, this point, okay, this point, the instantaneous acceleration of this point would also be A upward. This is the main point that you have to understand. If this body is moving upward acceleration A, this body is connected by the Maxwell disc by a rope, okay, and the point of contact is nothing but this one, and the acceleration of point of contact or the linear acceleration of point of contact is nothing but A in upward direction. Once you understand this point, this question is almost over. I can easily say that linear acceleration is equals to alpha into r, isn't it? Okay. And if I make a rotational equation means the torque produced by this tension force. The torque produced by this tension force is nothing but T into R, or R cross T. R cross T is equals to moment of inertia of this entire Maxwell disk into angular acceleration of this Maxwell disk, isn't it? So I can write TR by alpha, sorry, TR by I is equals to alpha, or angular acceleration. What is the value of T, or what is the value of tension force? I already found out, mg by 2. or mg by 2 into r by I is equals to angular acceleration alpha. Okay, find out the tension. Acha, the tension is already found out. Find out the tension and the acceleration of the bar. I must also find out the linear acceleration of the bar. See, the value of tension is found out. Okay, the value of tension is found out. I have to find out the linear acceleration. So if I find out the angular acceleration, what is the value of linear acceleration? Linear acceleration is nothing but alpha into r. So linear acceleration out here is nothing but alpha, which is mg by 2 into r by I into r, or alpha into r. Okay, or linear acceleration is equals to mg by 2 into r square by I. So the linear acceleration is given by this value, the tension force is given by this value, and this is the end of our question.